All right, we are looking at our last section for Chapter 7. We will spend the next 2 days reviewing and then taking a test, all right, before spring break. Our topics today, we are looking at natural logarithms. We're basically going to do the same things we've been doing, but with natural logs instead of common logs, okay? So we're going to look at evaluating and simplifying natural logarithmic expressions, and we're going to look at solving equations using natural logs. So the first thing, it says the function y equals e to the x has an inverse called the natural logarithmic function. We can write it y equals log base e of x or y equals the natural log of x. We've talked a little bit about those two keys on your calculator, right? LOG means common log or base 10. ln means natural log or base e. So I'm going to go back and show you where this is coming from. If we start with y equals e to the x, and I said find its inverse, what's the first step when we find an inverse? Switch the x and y. So if I switch the x and y, it becomes x equals e to the y. Okay. If I rewrite this logarithmically, I would say log base e of x equals y, which is what I've got right here. Log base e of x equals y. So this is the inverse of that one. Okay? When we look at the graphs, this is our exponential graph, okay? Y equals e to the x. And this one here is our natural log graph. We've talked about inverses before, being reflections over that diagonal y equals x, right? Okay. Would this graph, let me rephrase that. If I had said graph log base 3 of x and compare it to the natural log of x, your graphs are going to be almost the same. Because in the second one, your base is 2.718, and here our base is 3. So very, very similar graphs. All right. So let's look at doing some condensing. You can expand and condense with natural logs the same way we did with regular logs. So I have 2 natural log of 15 minus the natural log of 75. When I'm condensing this into a single log, what's the first thing I would do? Okay, put that 2 back as a power. Right? It goes back as an exponent or power of the 15. So we have the natural log of 15 squared minus the natural log of 75. And when we condense subtraction, it goes back into division. So this is the natural log. What is 15 squared? So we have 225 being divided by 75. What is 225 divided by 75? 3. So this becomes the natural log of 3. Okay? All right, let's try another one. We have the natural log of 7 plus 2 times the natural log of 5. Again, any front numbers you're going to put back as powers. So this 2 is going to go back as 5 squared. When we do addition and condense it back down, it becomes multiplication. So this is the natural log of 7 times 5 squared. What's 7 times 25? 175. So we have the natural log of 175. Okay? I'm going to pause the recording. I want you guys to try the next 2. All right, let's see how you did. I would put the 3 back and the 2 back as powers. So we have the natural log of x cubed minus the natural log of 2x squared. Now notice I put parentheses because all of that 2x is getting squared. Subtraction condenses into division. So we have the natural log. On the top, we're going to have an x cubed. For the denominator, we'd have what? 4x squared. Yep. And then can we reduce anything? Take some x's out. So we end up with the natural log of x divided by 4. All right. The third one, again, putting powers back. We have the natural log of x cubed plus the natural log of y squared plus the natural log of 5. And the addition is going to condense back into multiplication. So we'd end up with the natural log of 5x cubed y squared. All right. So the condensing and expanding, same rules that we had for regular logs. Okay. All right. It says you can use the inverse relationship between the functions y equals the natural log of x and y equals e to the x to solve certain logarithmic and exponential equations. When we solved exponential equations, we took the log of both sides. When we solved the log equation, we rewrote it exponentially. We can do the same thing with natural logs. All right, so for the first one, we have the natural log of x minus 3 squared equaling 4. What is your base when you see ln, natural log? Base e. Okay, we use the abbreviation ln, but I could have written this as log base e of x minus 3 squared equals 4. Okay, it means the same thing. So picture rewriting it exponentially. All right, it's a log equation. We're going to use its exponential form to solve it. So e to the 4th power gets us all of that stuff. Right, e to the 4th gets me the quantity x minus 3 squared. Now, if I'm trying to solve for the x, I need to get rid of that square. How do I undo a square? Square root it, yep. So I'm going to square root both sides. Remember that when you square root, you have to consider both the positive and negative root. On the right-hand side, the square and the square root cancel each other. So we have x minus 3. What do we get on the left side? Plus minus e to the 2nd power. Now, I want to make sure you're understanding how we're getting that 2nd power. A square root means a half power. So this means we have e to the 4th to the half, right? And power to a power, we multiply. 4 times 1/2 is 2. Okay. Then I can add the 3 to the other side. So I have plus minus e squared plus 3 equals x. That would be the exact answer. So if they didn't ask for a decimal or rounded answer, that would be precise. We do have to check to see if they're extraneous. So we have to make sure that when we plug them back in, we're not trying to take the log of a negative number. So what would e squared equal? $7.3891. So about 7.4? Yes? What do we get if we add 3 to that? So 10.73, no, 10.3891? Okay, and then what is negative 7.3891 plus 3? 4 point. Okay, so those are my two possible x values. If I plug them back in, will I have any trouble? In other words, will I be trying to take the log of a negative? That square means it doesn't really matter what's in the parentheses, right? As soon as I square it, it's going to come out positive. So both answers would be given as solutions. They both will work. All right, next one. I'm going to have you guys try the next two. I'm going to pause the recording, give you some time. For the first one here, what is our base? E. So picture doing your circle, right? We'd have e to the 2nd power equals x. Okay, again, if I need an exact answer, you'd leave it like that. If we do the approximation, we'd say e is approximately 7.3891. Okay. For the second one, again, our base is e, so picture doing your circle. e to the fourth equals 3x plus 5. That quantity is squared. To undo the square, we have to square root both sides. Okay, so we're going to have plus minus the square root of e to the fourth equaling 3x plus 5. When I square root e to the fourth, we said we got e squared. So plus minus e squared equals 3x plus 5. To solve for x, I'm going to subtract the 5 over. And then I have to divide out the 3. Okay? Again, that would be the exact answer. What's some approximations for those two values? .796. Yes? And what's the other one? Okay. Again, plugging them in. It really isn't going to matter if this part here in parentheses is positive or negative. As soon as we square it, it's going to be positive. So they both will work. How is C different? There's 2 natural logs on that side. What was our technique yesterday? Condense it back down into 1. All right? It's an addition, which means we're going to condense it into multiplication. So we have the natural log of 2x times 3. So the natural log of 6x has to equal 2. Rewrite it exponentially. So e to the second power gets us 6x. And then divide out your 6. Whoops. All right. So e squared we said was about 7.4. Dividing by 6 is going to be a little bigger than 1. Okay. Is that going to be a problem if I put in x of 1 point something in there? No. Should be fine? Okay. So again, e squared divided by 6 would be the exact. What is your approximation? All right. All right. We are going to shift now to solving exponential ones that have multi-steps here. What would our first step be? Subtracting the 2 would make sense. Subtracting the 2 gets me 4e to the 2x equaling 14. Then what do you think we should do? Divide out the 4. So e to the 2x equals 14 divided by 4, which is 3.5. Now, what was our technique when we were solving exponential ones before? If we couldn't get a common base, we used logs, right? We took the log of both sides. I can take the common log of both sides. It will work. And I can do the same process I did before. So I could take the log of e to the 2x equaling the common log of 3.5. What did we do then? The powers went out front, so we had 2x times the log of e, common log of e. And then I could divide the common log of e out. Yes? You guys don't have to write this down because I'm going to show you a different way. It's faster. Once I get that answer, then I have to divide out the 2. Correct? Okay. When we see an e in our exponential equation, when e is the base, it would make sense, instead of to use a common log where it's base 10, to use a natural log, because then our base matches. And do you remember what happened when we said we had the log base b of b to some power? Our answer was just the power, right? Because we're saying b to what gets me b to the x? My answer would have to be an x. Yes? Well, if I take the log base e of e to the 2x, log base e of e to the 2x, that whole side just becomes what? The 2x. Yes? And log base e means natural log. So what I'm going to do is take the natural log of both sides. And then the left side, we said, just becomes a 2x. All I have to do on my calculator is take the natural log of 3.5 instead of having to do that. Okay? And then divide your answer by 2. What decimal do we get? 6264? We okay with that? Yes? All right. Our next one. Is there anything we have to do first before we can take the log of both sides? No pieces to move? All right. Because there's an e in it, what kind of log are we going to use? All right. So the natural log of e to the x minus 2 equals the natural log of 12. What happens on the left side of that equation? We end up with the power, yes? Our base is e. E to the x minus 2 gets me e to the x minus 2. So my answer is just x minus 2. Once I know the natural log of 12, what would I have to do? Add the 2 over. So go ahead. 2 plus the natural log of 12, what do we get? .4849, something like that? Yeah. Okay. All right, I'm going to pause the recording. I want you guys to try the next 2. All right, what was our first step? Divide out the 2. So we have e to the negative x equals 10. All right. Then take the natural log of both sides. On the left side, we end up with negative x. So once you find the natural log of 10, just do its opposite. So you should have x being negative 2.3026. Okay with that? All right. Last one, what did you do? Subtract it. So e to the 3x equals 10. Natural log of both sides. We have 3x equaling the natural log of 10, and then divide out the 3. So you should have gotten 0.7675. Questions on any of that? So really the same steps you've done before, just with natural logs instead. Base E. All right. 2 quick word problems for you. It says natural logarithms are useful because they help express many relationships in the physical world. Our first example, it says we have a spacecraft that can attain a stable orbit 300 kilometers above Earth if it can reach a velocity of 7.7 kilometers per second. The formula for the rocket's maximum velocity in kilometers per second is v equals negative 0.0098 t plus c times the natural log of r. It says the booster rocket fires for t seconds. So t is time, and the velocity of the exhaust is our c value in kilometers per second. It says the ratio of the mass of the rocket filled with fuel to the mass of its mass without fuel is r. Suppose the rocket shown in the photo has a mass ratio of 25. That means r is 25, yes? It has a firing time of 100 seconds. So that's our t value. And it has an exhaust velocity as shown. So in the picture here, we are told that our c value is 2.8. So when I look at this big complicated equation, I'm given a value for t, I'm given a value for c, and I'm given a value for r. All I have to do is plug them in. So V equals negative 0.0098 times T, and T was 100, plus our exhaust velocity was 2.8 times the natural log of the mass ratio, 25. All right, grab your calculators and type that in. So your calculation should have given you a velocity of about 8.03. Yeah. Yes? All right, and that was in kilometers per second? All right, it told us that we can reach a stable orbit if we can get to at least 7.7 kilometers per second. We got to 8. So, can that spacecraft reach a stable orbit? Yes. All right. Our last question. You invest $2,000 into a bank that gives you continuously compounded interest of 6.7%. How long will it take you to double the money in your account? What formula did we have when we talked about continuous compounding? That was that PERT formula, yep. So A equals, final amount equals our principal times e to the RT power. What have they given us? They gave us the rate, 6.7%. We would convert that to a decimal. What's our decimal? Okay, so we're going to have e to the 0.067. Did they give me a time? No, that's what we're trying to figure out. Did they give me a principal, an initial amount? Yes. We had $2,000. And what else did they tell me? We wanted to double, so my final amount should be $4,000. What would you do for your first step? So did it really matter that we put 2,000 in? I could put any number in. If I wanted to double, it's going to come out to be the same answer I get here. Because my first step is to divide out the 2,000, I end up with this. Yes? If I wanted my money to triple, instead of a 2, I'd have a 3. Okay? Doesn't really matter how much I start with. It's the time it's going to take for it to double or triple. What would we do as our next step? We're trying to find t. Take the natural log of both sides. So the natural log of 2 equals the natural log of e to the 0.067t. What happens on the right-hand side? Okay, so we have the natural log of 2 equaling 0.067t. So we're going to take the natural log of 2 divided by 0.067. What do we end up with? So a little over 10 years to have our money double. All right. So our topics today were to evaluate and simplify logs that involve natural logs. Yes? We okay with that? Expanding, condensing, that kind of thing. And then solving equations that have natural logs. All right. Your homework, I am going to change this to be a 61, not a 62.